Hello. I have explained what is the endogeneity problem, and also I tried to give you an intuitive explanation for the endogeneity problem and the role of an instrumental variable which can fix the problem. So in the previous video, I have illustrated how it works using the example of wage and education. So let's put that a little more, put it into a little more formal text context. So then we observe X and Y and Z. In the graphical example, X was education, Y was earnings, and Z was some instrument. I'll give you an example later, just the new variable Z. And basically at the end, we want you to calculate this. When Z, the new variable, increases by 1 unit, how much will Y increase? How much will Y change? So using the total differentiation notation from the calculus, when Z changes by a little, Y changes this much. This can be decomposed into direct derivative. So how much Y increases with everything else being the same. This is the direct effect. And this effect, the second term, is through X. Z increases X and then X increases Y, right? This is effect of Z on Y through X. And the final term is through epsilon. So Z increases, then epsilon increases, and then epsilon will increase Y. So this is also an indirect effect through epsilon. So this is what I wanted to give you in the graphical illustration. And what we need in here is that the first term disappears. No direct effect on Y. So Z, the new variable, has no direct effect on Y. And another assumption we need is Z does not affect epsilon. The error term is not affected by Z. So if you cross out this, then the second term is the only term that determines the total differentiation. So dy over dz can be written in this way. Can be there is only one channel, and that path can be decomposed into two steps. Z affects X, then X affects Y. And what we want, the reason why we are considering this problem is because we want you to estimate this. We want you to estimate the effect of education on earnings. So this is what we want. This is what we want. So we are going to isolate this parameter by moving this to the other side. So then this is what we have in the end, right? How can you do this? How can you implement this? Simply, you linearly project X onto Y so that the slope captures how much X increases when Z increases. And similarly, you linearly project Y onto Z. So it also gives you how much Y increases when Z increases. So lambda captures this, pi captures this. Then beta is the ratio between them, right? By the way, this is just an intuitive explanation. In practice, we do not use this kind of method, and practically it will be much more complicated. So it is just on intuition. So now you have to understand what is the endogeneity, the definition, and why we cannot identify the effect of an endogenous variable. And then I want you to understand the role of the new variable, the instrument. And in this case, commonly we just say we use z, the new variable, as an instrument for x, instrumental variable for x. Or simply, or casually, we say instrument x is instrumented by z, or z is an instrument for x, or we use right, exactly. That's the same thing. So instrumental variable, the new variable, is referred to as the instrumental variable. Then, how can we find z? So then it seems that if you have a new variable z, then you don't have any problem. It's pretty simple. That is right. It's pretty simple in the end. But finding z is very difficult. That is usually your main job in your research. Yeah, if you can find a nice instrument for an important question, that will do your PhD. So if I cannot answer this question, if I knew this, then I would got a Nobel Prize. And then let's think about an example. Then what is the new variable? I have explained as if there exists a variable like that. And I'm going to show you interesting graph. So this is data from 1980 census, and for men born in the 30s. So, and it's from so you can find this graph from this textbook, mostly homeless textbook. So it's a small textbook and it is like $20, $30. So it's pretty inexpensive, affordable, and I strongly recommend this to those who are not confident in their mathematical ability. So it does not use much mathematics in this book, and still it explains a lot of important methodologies used in applied economics. So as to an econometrician, to a theoretical econometrician, this textbook is not enough. However, for an applied economist who would like to use some econometric techniques, then this is a must read. And it is well written, so easy to read and easy to understand, and a lot of examples. Or if you think it's too difficult, the same authors have an easier version. This is for undergraduate level, and this is for PhD level. But you know, the English is a professor at MIT, so it could be a little bit too difficult for some of you. And then maybe this mastering matrix could be better. Anyhow, just recommendation. And let's go back to the graph. What's interesting here is, from the data, they calculated the average years of education by quarter of birth. So think about this. Calculate the average education for those who were born in the first quarter of 1930, and second quarter, third quarter, fourth quarter, and then first quarter in 1931, second quarter, third quarter, fourth quarter, and first quarter in 32, second quarter, third, fourth. What's surprising here is, I would expect the quarter birth means nothing, has no effect on education, but there is a clear pattern. First quarter is consistently lower than the first is consistently lower than fourth quarter. So right, so increase from 1, 2, 3, 4, then drop. 1, 2, 3, 4, drop. 1, 2, 3, 4, drop. So there is a clear drop, say between 4 and 1, 4 and 1, 4 and 1, 4 and 1, right? This pattern is really strange. I'm going to explain why that happened. But anyhow, this is a first observation. And second observation, you calculate, again, from the same data, they calculate the average weekly wage, average wage by quarter of birth. Surprisingly, I would guess quarter of birth has nothing to do with wage, but there is a pattern. So first quarter born men have consistently lower wage. 1, 2, 3, 4, drop. 1, 2, 3, 4, drop. 1, 2, 3, 4, 3, then drop. 1, 2, 3, 4, drop. So it's kind of, there is a clear pattern. Then so it is interesting, but we use this strange pattern to identify the relationship between education and earnings. Quarter of birth itself is less interesting. It is interesting. It may be an important variable, but what we want to estimate in general is the effect of education on earnings. So let me explain what's going on here. So it is what we wanted for from the new variable. So first observation, we just find that first quarter born men have lower education than fourth quarter men by 0.1 years. So I did not calculate, just say that simply 0.1 year lower than fourth quarter. And second observation, second graph says first quarter have lower wage than fourth quarter by $0.02. Also, just say $0.02. It's not I did not open the data, so just say you observe some differences. Clear there are differences, and then those are observations. I do not say anything why this happened. And assumption one, first assumption I would make is that quarter of birth does not have any direct effect on wage. I think it's pretty obvious. When you hire someone, your wage is not determined by your birthday, right? No one cares about your birthday when you negotiate the salary. So quarter of birth has no direct effect. Direct effect does not exist. And second assumption is that quarter of birth does not have any effect on ability, unobserved ability. I think it's also very plausible, because if this is wrong, that means you expect babies born in, like, say, born in winter are like less smart than the babies born in like fall, for example, summer. I'm not so sure if that kind of thing exists. Actually, I'm working on that topic, but there is some kind of pattern, seasonality, but it's hard to imagine why quarter birth affects ability. So we assume it does not affect ability. It's plausible. And under those two assumptions, we can identify, we can say that the effect of quarter on wage is observed, but that's only through education. So there is no direct effect. There is no indirect effect through epsilon. That's exactly what we wanted, right? It satisfies those two assumptions. And then what you can do here is, it looks like that 0.1 year increase, 0.1 year increase in education, which was caused by the quarter of birth. So 0.1 year higher education implied $0.02 increase in their wage. So 0.1 year, $0.02, which can be extended, can be extrapolated to say that if the change was 1 year, like 10 times greater than this, then the change in wage would be 10 times greater than this. So 1 year increase in education will increase the weekly wage by $0.02. That is our conclusion. So this is the effect of education on wage, and beta is 0.2, right? This is how the instrument variable can control for the endogeneity problem. It's very interesting, very surprising result. Then let me explain what's going on, why this happens. So think about two kids kid A and kid B. Suppose that everything else being the same. So these two kids are identical guys, or you can think them as twins. But the one of the twins was born in December 31st, 2000. And the other was born in January 1st in 2001. So even though their birthday is virtually the same, actually pretty much the same, but the problem is their calendar year is different by 1 year. So the first kid was born in 2000 and the other born in 2001. So the calendar year, this difference may change the year they enter the school. So if you are born in 2000, you can enter the school in September 2006. And if you are born in 2001, you enter the school in 2007. By the way, it's not real. So in practice, the cutoff day is not January 1, but for simplicity, I'm going to do this. So actual practice does not work this way. My son is going to school next year. So still, I don't know. I have no idea what's going on. Anyhow, I don't know the rule, but it's reasonable. There must be some kind of rule, cutoff rule. On the other hand, what's interesting here is at the time, so it's man born in the 1930s, is like 90 years ago. At the time, the compulsory schooling law says that a student cannot drop out of school until their 16th birthday. So 16th birthday, they have to be in the school until their 16th birthday. Then, so think about this. The beginning year, entrance year, differs by 1, but the minimum year, so the compulsory schooling, mandatory schooling, is the dropout date. If they are going to drop out on their 16th birthday, then this is the same. So the end point could be the same. So it does not matter. So the kid A can drop out of the school on December 31st, 2016, and kid B can drop out on January 1st, 2017. So 1 day difference. So the end point, the last day on school could be different by 1 day, but the starting point is different by 1 year. So this causes the difference of the education. So the minimum education, so you are requiring say 16 years of education for December kid, but you are requiring 15 years of education for January kid. So that's the authors explain why this happened by this institution. It's very interesting. I'm not so sure if because I do not know the rule exactly. But it makes sense. That's an interesting example and a nice textbook example. So, by the way, this paper was sensational at the time, but these days it is criticized a lot. So if you are interested, you need to study more. It's been 30 years ago. The paper has been published 3 years ago. So in the next video, I am going to be more rigorous again. So far I gave you intuition and example, but in practice, how it works is a little bit different, and there are two different approaches to identify and to get to the same goal, the identification. So I'm going to explain that in the next video.